Last time we defined epsilon NFA and it's just like NFA, but the only difference is that now we can have epsilon transition. That means even without reading a symbol, we can change from one state to another. And this was the acceptance criteria informally. And to formally define this, we so first of all we need to define this transition function delta, and this is again almost same as the transition function for NFA, just we have this epsilon also along with the symbols. So this was the mental picture, and then in terms of delta we define this extended transition function using this equation, right? And again this equation came from actually this picture. So with all this definition and all, then we finally proved this identity. So this identity holds, see that for both NFA and epsilon NFA. So for NFA you can actually use the delta here instead of delta hat, but here you need delta hat because in terms of delta it will look something like this, right? So now our goal is to show that this epsilon NFA and NFA without epsilon transition, so they are equivalent in power. So how do we show that? We have to show that any language which is accepted by one model is also accepted by another model. So from here to here is quite easy because epsilon NFA is a generalization of NFA, right? You take a NFA, it is already a epsilon NFA where there is no epsilon transition. So in this direction there is nothing to prove. The interesting part is to prove this direction, right? So if you are given an epsilon NFA, then how do you construct a epsilon equivalent NFA without epsilon transition? So that means you construct NFA which accepts the same language, right? And to do that we will use this identity. So this will be important. And we also defined this epsilon closure, and what was that? So it was basically this. So you start epsilon closure of Q is the set of state that you can reach. So this without consuming any symbol, right? So using transitions, using only epsilon transitions. So all the states that you can reach, so that set is the epsilon closure of this Q. So just keep in your mind all these definitions and equations, and let's proceed to show the equivalence of these two models. So see, if we are given, say, this epsilon NFA, we want to construct NFA without epsilon transition. Again, both are 5 tuple, right? As I said, here the only difference is that here you can take epsilon, here you cannot. So we want to construct a equivalent NFA. So that means, in some sense, whatever this is doing, this should also do that. And to make it slightly more formal, we can say that whatever path you can construct here on some input string, you should have an analogous path here also, right? You cannot have the exact same path because it doesn't have epsilon transition. And to ensure that, first think of path of length 1. So that means just a transition on single symbol, right? So now here, since you do not have any epsilon transition, so here on a single symbol you can just have this sort of transition from one state to another by consuming one symbol, right? And this thing should simulate a path in this given epsilon NFA, which also consumes just one symbol. But here what can happen? So here the path in general can look like this, right? So initially you can take some chain of epsilon transition, so you can have multiple transitions here. It can be 0 steps also, so this P and Q can be same, right? So whatever, I mean, without consuming any symbol you reach this thing, and then you consume a symbol, and then again you can take epsilon transitions, or these two can be the same thing. So in that case it will be 0 steps. It can be 1 or more steps also. So yeah, so you need to kind of simulate this path using just this transition, right? So what is this path? If you see the definition of this thing, delta hat. So delta is for the epsilon transition, right? And this delta n is for the NFA without epsilon transition. So if you just take this delta hat with one symbol, so in general it can take a string, right? But here if you just consider one symbol, so this is what it is, right? So how did we define this thing? So this is precisely the set of states that you can reach by processing this string. In this case, the string is a symbol starting from state Q. So you consider all this kind of paths. So there can be multiple such paths. So there can be a set of state here instead of just this single S. So that is what this thing is. And here also you can have multiple thing with, say, a transition with labeled with A, and this is consistent with our equation that we got, because what was the equation? So you see that this P is in the epsilon closure of Q, right? And then you are taking a single delta here, because there is a single step, delta in epsilon NFA. So you take the epsilon closure, then a delta, and then again a epsilon closure. So that was the equation in fact we got here. So this is what we derived. So you see that you take P in epsilon closure of Q, then you take a single delta, and then over this again you take epsilon closure and take union of everything. So this equation is this picture with all the possible such paths, right? So once we have this, so now it's very promising to define our delta n, so the transition function for this NFA without epsilon transition. So now we define its transition function as this, okay? So this delta, this E is given, right? So that means this is defined based on this. And this is a function of the, so if we just restrict this here, so this A, again we are talking about non-empty strings here only, okay? So then also it will hold. So in general in E we can have epsilon here, but here we are only considering this non-empty, this symbols, right? So then we define this as this. So once we define the transition function, our n is fully defined, because not fully defined. So we will see that there is a question of how we define this final set of final state. It may not be same as this, but the set of state is same, the input alphabet is same, starting state is same, and we have defined this thing. So with this what do we get? So we are actually simulating a chain of transition on symbol A as a single transition on symbol A in our n. So this should be pretty clear. Okay, so as I said, we had this definition, and this P is this P and this R is this R. Okay, so I have already explained that. So now if we have this, then we can prove that their hat is actually equal. Okay, what is this? Sorry, this should be A. This should be A. There's a typo here, right? Okay. So then we can prove this. Okay. See, we have defined this delta n based on this thing. So once we define this delta n according to our equations for NFA, we can also have this delta n hat. So that will be for this NFA n, but for strings here, right? So this delta n hat so will be the set of states that you can reach by processing this input string w starting from state q, and that set of state we are claiming that is exactly same if you do the same thing in the this epsilon NFA. So you start with q and you process this w, so then you will get the same set of states, and that is pretty clear because we can actually break this down into individual symbols, and for each symbol that relation is respected, right? So we are exactly simulating this thing with this. So even without looking at this proof, you can prove this thing. So, but a very crucial thing is that here we need at least one symbol, right? So if this thing is epsilon, so here it is not epsilon, right? Because if it is epsilon, so if it is epsilon, say, then this entire thing will be epsilon chain of epsilon transition, right? So that means even without consuming a symbol, it can change from here to here, but you cannot mimic that here, right? Here you have to consume one symbol. So you cannot have a epsilon here because this is the n, so NFA without epsilon transition. So we need at least one symbol here, right? So this will not work for w equal to epsilon. So this will work for non-empty strings because then we can take the base case as where this consists of just one symbol. So length is 1, so it is just one symbol, okay, for some symbol in sigma, and then we can do a induction step. So it just one line thing, and it follows from the equations, it follows from the common sense also, and if you want to put the equations. So these are induction hypothesis because here we can express this in terms of xa, where x is a smaller string, a shorter string, but a should not, see, this x should not be empty, okay, because the base case is where this thing is of length at least 1, length 1 in fact. So with this thing we can see that this equation holds. So this equation, this thing holds. So for any string w, if you start with q and if you process this w, the states that you can reach in this E is precisely the set of states that you can reach in N, right? So now what else do we need to do? Now can we just put the same set of final states and be done with that? So it seems so, because the transitions are fully kind of simulated, but the only glitch, as I said, is for the epsilon string, because then this equality does not hold. So to manage that epsilon string we need to do some more work. So right now, what do we have then? So this theorem is just saying this, that if you start with Q and process any W, and if you can reach S here, so then you can do it here also. In fact, it's if and only if. So if you can reach S by processing W from state Q, then you can do that in N. If you do that in N, then you can do that in E. But this should require one or more steps, right? So that is important. So that is why this W is not equal to epsilon. Okay. So this one step is required. So this cannot be epsilon. So this is what we have so far, right? Okay. So let's just consider this example. So from Q0, do we have a chain of transition like this for, say, symbol A here? So we do have this C. You can take this epsilon, and then you can take A back to this Q0, right? So in fact, that means you are considering all the states that are in epsilon closure of Q0. So epsilon closure of Q0 is what? Q0 itself, also Q1 and Q2. But from Q2 and Q0, there is no transition on symbol A, right? So you can take this epsilon transition to Q1 and then take A and come back here. So this corresponds to this kind of a path in this epsilon NFA. So if you are considering equivalent NFA without epsilon transition, you should introduce this path from Q0 to itself labeled with A. So similarly for C, that will be the same thing. So if you have normal transitions on C from here to here, those transitions you already have also in N, right? Because they are considering just this part. So this is just a special case where this has 0 steps and this has 0 steps. So these transitions are fine. So this and this and this. So they are just taken from here. Also for this C you have this C. But for this thick transition, for example, this transition, why do we have this transition with B? Because you see, we can take this epsilon here, so from Q0 to Q1, and then can take this B to reach Q2. So that means just by processing B, we can reach from Q0 to Q2. So that is why we have this thing, right? So in this way you can construct this NFA without epsilon transition, because we are just consuming everything into a single transition here, right? But still the question is how to set the set of final states. So here I haven't shown any final state, so it's not about any language so far, but if I put some final state here, so will it also work here if I take the same final states? So that is the question. So now you see the acceptance criteria for this epsilon NFA is that if you can reach any final state by processing the input string, right? So let's just for any string W, if you have this hat Q0W intersected with the final thing, if that gives you some non-empty thing. So now if we take this W to be epsilon, Okay, so just consider this epsilon string, because as we showed, so epsilon may pose some problems. So then how does this thing simplifies? So then it just means that there should be some final state in the epsilon closure of W0, right? Okay, because this is what, by definition, this is epsilon closure of Q0, right? So if you see the definition of delta hat for epsilon NFA, and that definition comes precisely from the idea that you can reach this set of state using just epsilon transition without processing any symbol, right? There can be just but it can be 0 step, 1 step, or multiple steps. So it can be just this. So it will always include this Q0, and you can take one or more epsilon transitions, and those things will be this. So you can have this thing, 0 or more steps. And if you can reach a final state in this fashion, then this epsilon is accepted in your epsilon NFA, right? So epsilon is accepted in your epsilon NFA if and only if the epsilon closure of Q0 contains some final state. Okay. Okay. So if epsilon closure of Q0 contains some final state, then and only then this epsilon NFA E accepts epsilon. So what was the condition for NFA? So the NFA was, again, it looks almost same. The only thing is that this the definition of this is different. So for NFA, what is this? This is a set of states that you can reach without processing any symbol in 0 or more steps, but here it has to be 0 steps, right? Because in order to make any non-zero steps, it has to consume some symbol. So this is just by definition, again, just this Q0, right? So yeah, because for just NFA without epsilon transition, we have this by definition, right? And by this, it means that Q0 itself should be in the set of final state. This itself should be some final state. So the automata, you can have other states, but this initial state, this starting state, is also one of the final state. So this is the condition. This is the condition for accepting this empty string in some NFA, in any NFA, right? Okay. There is some typographic error in the presentation, minor thing. So in couple of slides here, you will see that I have written it as Q, but Q is wrong. So it should be Q0. And also in this slide the mistake is there, and here also this Q0 is also written as Q, but Q is wrong. This should be Q0, and here also the same line actually for so here also there is a error. This should be Q0. This should be Q0, and here also this should be Q0. I have written it as Q, so which is wrong. So please take this as take this into notice. String in some NFA, in any NFA, right? Okay. So once you grasp this, let us now just try to prove that we can construct this equivalent n. Now as we have already proved this thing, okay, and this followed from here, right? So we just formally proved it here in this claim, okay. So this thing, so since we already have this, okay, so if we just take Fn to be equal to F, right, so then this condition is automatically followed, right? So this is non-zero if and only if this is non-empty if and only if this is non-empty, and this was the acceptance criteria for NFA without epsilon transition. This is NFA with epsilon transition. So if we take this, then this works for W, where W is non-empty, you remember. So the claim required that this W must be non-empty, okay. So what we have is that if we choose Fn equal to F, so Fn is the set of final states in the NFA without epsilon transition that we are trying to define. We are trying to make it equivalent to this E, right? So if we choose this, then for all non-empty strings, this thing works, that if it is in the language accepted by N, then it is also in the language accepted by E. So that works fine for all strings except this epsilon, this empty string, right? So we are almost there just by this. Now, if this thing, the language accepted by this E, this epsilon NFA, does not have epsilon as part of its language, so then actually we are done, right? Because then this is trivially true, right? Because this epsilon is not anyway in the language of LE, so then it's fine. And you see, it is not in the language of epsilon, so that means even here, so if you are considering some Q0 here, okay, so that cannot be, a final state here, because then it will accept epsilon, right? So, and if we are taking F equal to Fn, then from here we also get that Q0 is not part of Fn because they are equal, and so that means it's not in this language also, because that is what the condition for epsilon being in the language of this N. So this was the condition. So this is not satisfied. If this is true, then we can see that by that this epsilon is also not in the language of N, and we do not need to worry about epsilon at all, and we can just take this to be equal, and just by this thing and this thing we have this equality, right? The difficulty comes when this epsilon is in the language of this epsilon NFA, and there also we can have slightly two different cases. So as we said, this epsilon, so what if this epsilon is in the language of this epsilon NFA E? Now, this is in the language if and only if this is true, right? That is what we saw in the previous slide. Now, in the NFA without epsilon transition, this epsilon is in the language if and only if this is true. That also we saw in the previous slide. Now, how do we reconcile this two slightly different equations? See, if this is true, then if we want to make these two languages equal, right, we must also have this. Okay. Now the question is, suppose this epsilon is so that means suppose this is true, but this is not true. Okay. And when is this possible, that this E is actually accepting epsilon, but the starting state is not a final state? So this is possible because suppose you have Q0 here. Okay, this is not final, right? But you can have, say, a chain of epsilon transition and then have a final state. So then this epsilon will be in the language of LE, but this Q0 is not actually a final state, right? So that means this final state is in the epsilon closure of Q0, but it is not Q0 itself, right? So then this is satisfied, this is not satisfied. So we cannot take this Fn equal to F and hope. I mean, then it will not give us the same language, right? So we have to have this Q0 in our Fn, right? So then can we fix this glitch by just defining Fn to be F, and also we include, say, this Q0? Question is, can we do that? Now, without any further argument, if we are just doing this, then see, this may not work, because for the non-empty string part, we relied on the fact that they are equal. So that is why for non-empty string it is accepted by n if and only if it is accepted by E. So it's if and only if condition. So there we required this, and then to accommodate this equality for epsilon, we are slightly changing this Fn. So now this we need to keep this part also intact, right? So now can we slightly prove this thing? So see, this thing worked if epsilon is not part of the language accepted by E. So now can we prove this, that if epsilon is accepted by E, so with this added constraint, okay, can we prove that if now we define this Fn to be this thing, then for any this W, empty or non-empty, we have this. So then what do we have from the previous slide? We saw that if this epsilon is not part of the language accepted by E, then we can just choose Fn to be equal to F, and then we have the same language accepted by N. So if this is the case, then we choose this and then we are done. But if this epsilon is part of the language accepted by E, then we are choosing this Fn to be F, and also we include this Q0, and now we want to prove this assertion. So this is the acceptance conditions for N, and this is the acceptance criteria for E, and we show that some string is accepted in N if and only if it is accepted in E, right? This should hold for both empty and non-empty string. Okay, and here we are actually assume that this is the case. So if this is the case only, then we are defining this, and then we are trying to prove this. Okay, so we can do this because this is given. So depending on what this automata is, and whether epsilon, the string epsilon is accepted by this or not, we can define this accordingly. So if epsilon is accepted, is not accepted by this, then for this we define it like this, and we are done. And if it is accepted here, so then we are defining it like this, and then we are trying to prove this. Okay, so for this part, for this part of the proof, we can just we have this assertion that epsilon is part of LE. So that means we have some state in F which is in the epsilon closure of Q0, because that was the condition in previous slide. If you yeah, so here, so this is true if and only if this thing is in so the epsilon closure of this contains some final state, and final state in E, right? F, not Fn. So we can assume oh, we also have that here. So we can assume this, and depending on that, we are trying to prove this thing both for W equal to epsilon and W not equal to epsilon. Now, just by including this Q0 in Fn, we ensured that epsilon is accepted by this n, right? Because your starting state is also a final state in n. So that was the condition for accepting epsilon in n. So just by this choice, we have that epsilon is accepted by n. So if W is equal to epsilon, then both machines agree. Agree means both of them are now accepting epsilon. So epsilon is done. So the concern was by since we are trying to fix it for epsilon, so did we mess it up for this non-empty strings, right? So now for non-empty string, we also need to show that this assertion holds, this if and only if holds. And for non-epsilon, non-empty W, we again break this into two different cases, right? So one is that there is a possibility that after processing W, starting from say this Q0, you may come back to Q0, or there is no path from Q0 to Q0 on W. Okay, so here it is saying that if you start from Q0 and if you process W, you can have multiple paths, but none of that path can lead to this Q0. So if this is the case, so then you see that it's equivalent to saying that this set doesn't contain anything or this set contains something from F if and only if this contains something from this Fn. Because what was Fn? Fn was F and also this Q0. But since we are already assuming that there is no path in this E to go from Q0 to Q0 on W, so then this is automatically satisfied, right? Because you see we have this for any Q, right? So here in fact we are using a particular Q which is Q0 starting state, right? So if this is equal to this, and we know that this does not contain Q0, so that means it says that okay, now it can contain some state from Fn if and only if it contains something from this F part, not this Q0. So this case is done, and then the remaining thing is just if there is a path from Q0 to Q0 on W on this epsilon Nfa. So again, by this equality, since our W is non-empty, we have that there is also a path in N also, right? So this picture in E means that there is a path, okay, sorry, there is this path on W which starts from Q0 and comes back to W. And that means also in N we have this path which starts from Q0 and comes back to Q0. Now you see, since this epsilon is in language of this epsilon Nfa, so that means this epsilon closure of Q0 contains some final state. So that means from here there is a chain of epsilon transition which leads to a final state. So this path has to be there because this is our assumption on this part, right? Now if this is the case, okay, so you see that this W is accepted in E, right? You process this W and then you take this path and go to some final state. So W is accepted here. And here also, since this Q0 is part of Fn, this W is accepted, right? So in both cases, this W is accepted. If this is the case, then this W is always accepted in both the machines, right? So for this case also, the two machines agree. So here W may get accepted, may get rejected, but from here we know that if it is accepted in E, then it is also accepted in if and only if it is accepted in N. So that if and only holds here, and here also it holds because it's accepted in both cases, right? So this is for the non-empty string, this is for the empty string. So for all possible strings, now this thing holds. Sorry, here there's a typo. Here we should have a Q0, right? So here we should have a Q0 instead of Q, okay? So a typo here. Okay, so this gives us the proof, this completes the proof that these two NFAs are actually equivalent. So if you just want to avoid this picture and everything, so this is the formal proof. So how are we defining this N? So first of all, this Q sigma Q0 are same. Qn we are just defining as this thing. So Q hat on a single symbol. This is non-empty, right? So that we are defining as this single step transition for this N. And then how do we define this Fn? So if this epsilon closure of Q0 contains some final state of this E, so that means this is equivalent to the case that epsilon is in the language accepted by E. But that we can see just by looking at the machine. So if this is the case, so then we include Q0 as part of Fn, also this all the final states of this E. Otherwise we just take this Fn to be F. So this means that this epsilon is not part of LE, right? And then the theorem is that their language is same. So again we divide it into two cases. So one is that epsilon is part of this LE, so then we take this, and by this condition, so by 1, so we have W is in this, if and only if this, and W is coming from sigma plus. So you remember the sigma plus is the set of all non-empty strings, right? But that is okay because anyway this epsilon is not in LE. And if this is the case, then our Fn is this, and then as we said, and we break it down into two cases where this Q0 is a part of this delta Q0W, and when it is not part of the Q0W, then again by 1 we have this, just by replacing, taking the special value Q0 for Q here, and if it is part of this thing, then the picture is interpreted as here. So that means this epsilon closure of Q0 that must be a subset of this thing, right? Because what is this thing? So all the states that you can reach from Q0 after processing this W. So you can reach Q0, and then from Q0 you can reach any state in epsilon closure of Q0 just by processing W. So this set of state is part of this set of states, right? So that means this W will be in the language accepted by this, right? And this is true because we are assuming that this is part of LE. So by this and by this 2, because this happens if and only if this closure contains a final state. So by these two things we have that this W is part of LE, and since this is anyway, so this is equal to so by this 2, sorry, by this 1, okay, this delta hat we can just put a n here also. I mean, so that means you can come back to Q0 from Q0 in n by processing W, and this is also part of or in fact yeah, so and this Q0 is part of Fn, right? So that is why W is part of Ln also. So putting everything together, we see that in this case, in this particular case, W is included in both this and this. So for all W and for all this case 1 and case 2, this equality holds, right? So if an W is included in Ln, if and only if W is included in LE. So that completes the proof. So just to give you now example, so this is epsilon Nfa, and now again we do the usual thing. So from here we need to figure out the transition on symbol A and B, right? So on symbol A, what will be the transition? So you can initially take epsilon transition, say this, and then take A. So from A to C there will be some transition. Yeah, from A to C we have this transition which corresponds to this path in our epsilon Nfa. So then say from C to E, if you see that, so you can take A and then take this epsilon transition. So both on A and B you should have a transition from C to E directly, right? So this is the transition here. So in this way you do all these things from C to B. And why should you have this AB from C to B? Because on AB from C you can go to D and then take this epsilon transition. So you have a transition from C to B on AB. So similarly all these transitions if you put here, so in fact this is given here also. So this thing and this thing, so these are all shown in this picture. So this is how we construct this thing, and then we see that here we have a final state which is in the epsilon closure of the starting state, right? If that happens, then we should make this starting state final in the epsilon in the NFA without epsilon transition. So we make this final. So if we did not have this, then we shouldn't have made this final state. All the other things would be kind of same, right? So this is how we convert epsilon NFA to normal NFA, and now you see that it's a general construction. So this works for all epsilon NFA. So now you have the proof that epsilon NFA is equivalent to NFA, but we also proved that NFAs are equal to equivalent to DFAs. So now this DFA, NFA, and epsilon NFA all are equal in power, that you know, right? I mean, if you can accept some language using one model, you can accept that language in using any one of these three models. Okay, so that concludes today's lecture.